All right, today we're going to tackle a classic problem that, believe it or not, shows up pretty much everywhere, from how the internet is built to how we analyze huge sets of data. The question is simple. How do you connect a bunch of different things in the cheapest way possible? So let's dive right in. Just imagine for a second that you're in charge of this massive project. You've got a whole list of cities, or maybe company offices, or even computer servers, and your job is to connect every single one of them with high-speed fiber. Now, you know the exact cost to lay a cable between any two of them. Your goal is pretty straightforward, but absolutely critical. Connect everything, but spend the absolute minimum amount of money. So how do you even begin to find that one perfect plan? Well, it turns out the solution to this puzzle has a name, and it has a beautifully simple strategy behind it. So let's break down the core of what we're actually trying to build here. Okay, so here's the main goal. We need to build a network where every single point can reach every other point. Think of it just like a road network connecting a bunch of cities. We want to make sure you can drive from any city to any other city, and we want to do it by building the least amount of road possible. Makes sense, right? Minimize that total construction cost. So this idea of the cheapest possible network has a formal name in the world of graph theory. It's called a minimum spanning tree, or just MST for short. Let's break that name down piece by piece. So let's break that down. First up, what's a spanning tree? Well, a tree in this context is just a way of connecting things without any redundant loops. See, if you have a loop, what we call a cycle, you could always just remove one of the connections in that loop. And guess what? Everything would still be connected. And hey, removing that extra connection saves you money. That's the whole point. So a spanning tree is a network that connects or spans all the points efficiently with no wasted cyclical paths. Okay, now let's just slap the word minimum on the front. For any given network, there can be many, many different spanning trees. Lots of ways to connect all the dots without cycles. The minimum spanning tree is the special one where if you add up the costs of all the connections you used, that total sum is the absolute rock bottom lowest it can possibly be. That's our holy grail. And here's a really cool, super powerful little rule to remember. For any network with a certain number of points, let's call that V for vertices, any spanning tree for that network will have exactly V-1 connections, or edges. So if you have, say, 10 cities, you are always going to need exactly 9 roads to connect them all in a tree. No more, no less. It's a neat little fact. So how do we find this perfect low-cost network? You might think this requires some kind of supercomputer, long-term, complex planning, right? But the secret? It's surprisingly simple. Just be greedy. You know, the real magic behind MSTs is that a greedy strategy is guaranteed to work. And this is incredibly rare in algorithms, and let's be honest, in life. Usually, a choice that looks good right now can totally backfire and trap you in a bad situation later on. But not here. For minimum spanning trees, making the best-looking local choice at every single step is mathematically guaranteed to lead you to the best possible overall solution. It's kind of amazing. The first reason this works is something called the cut property. Okay, so picture this. You draw a line, we call it a cut, that splits all your points into 2 separate groups. You're going to have a bunch of possible connections that cross over this line. The cut property guarantees that the absolute cheapest of all those crossing connections has to be part of a minimum spanning tree. It is always a safe move to add that edge to your final network. Guaranteed. And of course, there's a flip side to this cycle property. If you ever find a loop or a cycle in your network, take a look at all the connections that make up that loop. Well, take a look at the single most expensive connection in that loop. I can guarantee you that edge will never be in any minimum spanning tree. Why? Because it's the most expensive redundant link. You can always get rid of it, save some money, and everything stays connected. So, armed with this awesome greedy secret, computer scientists came up with 2 really famous algorithms to find the MST. They take slightly different approaches, but they both use that greedy logic to arrive at that perfect minimal network. Let's see how they work. Okay, so we have Kruskal's and Prim's algorithms, and you can think of them like this. Kruskal's is the global planner. It's like it's looking at a map from a satellite, seeing every single possible road at once, sorting them all, and then picking the best ones. Prim's, on the other hand, is more like a local explorer. It starts at one random spot and just grows outward, one connection at a time, kind of like a crystal forming. So let's zoom in on Kruskal's first. This one was developed back in 1956, and its strategy is it's beautiful. It's so straightforward. It focuses entirely on the connections, or the edges, themselves. The process is so simple, it's almost elegant. Step 1, you make a big ol' list of every possible connection, and you sort it by cost, from cheapest to most expensive. Then, you just start at the top of the list and go. Grab the cheapest connection. Now ask one simple question. Does adding it create a loop with the edges you've already picked? If not, great, keep it. If it does, just toss it out. You just keep going down your list, keep or toss, until you've kept exactly V-1 connections. And that's it, you're done. You've just built a perfect MST. All right, now for Prim's algorithm, which came out just a year later in 1957. And unlike Kruskal's, which kind of jumps all over the map, Prim's is all about building out from a single, ever-growing connected area. With Prim's, you start super small. Just pick any single point. Seriously, it doesn't matter which one. Now you look at all the connections leading away from that starting point to somewhere new. Which one is the cheapest? You grab it. Now you have a tiny little tree with 2 points. And the process just repeats. From anywhere inside your little connected bubble, you find the absolute cheapest path to a new point that's still outside. You add it, and your bubble gets bigger. You just keep doing that, always expanding your frontier with the cheapest possible link until every single point is inside your bubble. And that right there, that's the greedy approach in action, pure and simple. Okay, so we have 2 totally different but equally correct greedy algorithms. So which one's better? Well, like most things in computer science, the answer is, it depends. Okay, don't let this big O notation scare you. It's really just a fancy way of talking about how efficient an algorithm is, how much slower it gets as the network gets bigger and bigger. So for what we call sparse graphs, not a ton of connections between points, both Kruskal's and an optimized version of Prim's are pretty much neck and neck in terms of speed. But for dense graphs, where basically every point is connected to every other point, one version of Prim's can actually pull ahead and be faster. The best choice really just depends on the shape of your network. All right, pay attention, because this is a big one, especially if you're prepping for a coding interview. First, people always confuse MSTs with finding the shortest path, like what Google Maps does. An MST is about the lowest total cost for the whole network, not the shortest trip between point A and point B. Also, and this is a cool one, unlike a lot of other pathfinding algorithms, MSTs are totally fine with negative edge weights, no problem. And, of course, a graph has to be connected in the first place for you to find a spanning tree. And finally, no, Kruskal's isn't always better than Prim's. It all depends on the graph. Okay, this is all great theory, but you might be wondering, is this stuff actually used anywhere? In the real world? Oh yeah, absolutely. This is one of the most fundamental and useful algorithms out there. Well, the most obvious one is exactly what we've been talking about, network design. Laying fiber optic cables, building road systems, planning out pipelines, that's MST's 101. But it gets cooler. It shows up in data science for doing something called cluster analysis, basically finding natural groups in your data. It's used in computer vision to help a program separate an object from its background, and it's even used as a starting point to get good enough answers for way harder problems, like the famous traveling salesman problem. The minimum spanning tree is just this beautiful reminder that sometimes the simplest, most, short-sighted strategy of just grabbing the best thing right in front of you can actually lead to a perfect, optimal result for the whole system. And that really makes you wonder, doesn't it? When else in life is just being greedy the absolute perfect strategy?